Wide band pass filter. There are two types in the band pass filter depending upon the value of Q, which is nothing but the figure of merit or quality factor. If Q value is less than 10, then you will be treated it as a wide band pass filter, and for the wide band pass filter the bandwidth will be high, and whenever Q is greater than 10, then we will be treated it as a narrow band pass filter. The bandwidth of the narrow band pass filter is low when compared with the wide band pass filter. And if you observe the circuit diagrams for the wide band pass filter, here we are going to cascading the high pass filter as well as low pass filter. So the wide band pass filter is generated whenever you are going to cascading the high pass filter and low pass filter. Whenever you want to generate the wide band pass filter for the first order, then you have to cascade the first order high pass filter with the first order low pass filter. In the stop band, it generates the gain roll of is plus or minus 20 dB. Whenever you want the gain roll is plus or minus 40 dB, then you have to cascade the second order high pass filter as well as second order low pass filter. So if you observe this circuit diagram, here it will be represented as a first order high pass filter. And if you observe this, which will be represented the first order low pass filter. So whatever the design steps you have to use for the construction of first order high pass filter as well as first order low pass filter, you have to use the same design steps for the wide band pass filter. Okay, and coming to the gain, here both the high pass and low pass filters are cascading together. Whenever you want to calculate the total gain of the wide band pass filter, which is nothing but the product of gain of high pass filter and gain of low pass filter. Okay, here I am going to represent the magnitudes of the individual high pass filter as well as low pass filter. First, I am going to represent the magnitude of the low pass filter. Modulus of V0 by Vin is equal to AF1 divided by square root of 1 plus F by FH whole square. Similarly, modulus of V0 by Vin for high pass filter, which is nothing but the gain magnitude of the high pass filter, is represented as AF2 divided by square root of 1 plus F by FL square into F by FL, which is nothing but the magnitude. So whenever you want to represent the total magnitude, okay, which is nothing but modulus of V0 by Vin will be equal to AF1 into AF2 into F by FL divided by square root of 1 plus F by FH square and square root of 1 plus F by FL square. So AF1 into AF2 will be treated as AF. That's why I told you that whenever you want to calculate the total gain of wide band pass filter, then you have to multiply the gains of individual filters. That is nothing but first order low pass filter and first order high pass filter. Okay, high pass and low pass filter. And one more thing you have to observe in this case is for the high pass filter we are calculating the lower cutoff frequency, whereas in case of the low pass filter we are calculating the higher cutoff frequency. So whenever you are representing the frequency response of wide band pass filter, always FH should be greater than FL. So here I am going to represent the frequency response by using gain in dB versus frequency. Now it becomes like this. So here the bandwidth will be nothing but this is FL and here we are getting it as FH, and always FH should be greater than FL in case of band pass filters, and the maximum gain is occurred at AF, and the cutoff frequencies are gain is 0.707 into AF for both the cutoff frequencies, and which is represented the bandwidth. So the bandwidth will be equal to FH minus FL, and here the center frequency is calculated by using the formula FC is equal to square root of FL into FH, and while you are going to calculate the quality factor or figure of merit, you have to use the formula Q is equal to FC divided by bandwidth. Okay, so whenever they are asking you to design the wideband pass filter, then you have to write the circuit diagram and you have to write the individual operations for generating the transfer functions or gain for the high pass filter as well as for the transfer function or gain for the low pass filter. Here I represented directly the transfer functions for the high pass filter, low pass filter as well as for the high pass filter, and you all very well known. Why? Because in previous classes I covered the generation of transfer functions by using the first order high pass filter as well as first order low pass filter. So you have to write those two derivations. Narrow band pass filter, whenever the quality factor or figure of merit is greater than 10, then we will be treated it as a narrow band pass filter. One more important point I want to tell you regarding to the band pass filter is band pass filter consists of two stop bands and one pass band. It passes only a particular band of frequencies. That's why we are calling it as a frequency selector also. Coming to the narrow band pass filter, instead of using 2 op-amps in case of wide band pass filter, here we are going to be used only 1 op-amp, and the main features of the narrow band pass filter are, first one is it consists of 2 feedback paths. And the second one is the op-amp is used in the inverting configuration. Because of the 2 feedbacks present in the narrow band pass filter, we are also calling it as multi-feedback filter also. And coming to the circuit diagram, here the input is applied at the inverting input terminal of an op-amp. That's why the narrow band pass filter is operated in the inverting configuration of op-amp, and the resistance R3 is connected to the non-inverting input terminal of an op-amp, which is used as a bias resistance, okay, or compensating resistance, okay. And next, the important parameters regarding to the narrow band pass filter are FL, FH, and the maximum gain AF and the quality factor Q, and the components related to this parameters are represented as. For the simplification easy purpose, we are going to consider C1 is equal to C2 is equal to C, and the components related to the various parameters are R1 is equal to Q divided by 2 pi FC into C into AF, and R2 is equal to Q divided by 2 pi FC into C into 2Q square minus AF, and R3 is calculated by using Q divided by pi into FC into C, okay. And the maximum gain at the center frequency is calculated by using the formula AF is equal to R3 divided by 2 into R1 at center frequency FC. And for the narrow band pass filter, it has to satisfying always the gain should be less than Q square to Q square. Changing the center frequency. So FC is nothing but the original center frequency. FC dash is equal to new center frequency. The new center frequency can be obtained by changing the value of resistance R2, and the new value of the resistance R2 can be calculated by using the formula R2 dash is equal to R2 into FC divided by F dash C whole square. And there is an important advantage in the narrow band pass filter because of these two feedback paths. Without changing the bandwidth, without changing the gain, we can change the center frequency from one value to another value, which is the major advantage of the narrow band pass filter. So whenever they are asking you to design the narrow band pass filter, you have to use all these equations for the calculation of the components R1, R2, R3. Okay, all these things. And one more thing I want to represent for the narrow band pass filter is frequency response, which is always represented in between gain and frequency. For the narrow band pass filter, the bandwidth will be low when compared with the wide band pass filter. And here it is, the center frequency is FC. The gain is maximum at center frequency, and at the cutoff frequency it will be 0.707 into AF for both the cutoff frequencies, and it will be FL and FH. And here also the bandwidth is same, FH minus FL formula is same for calculating the bandwidth, but the value of the bandwidth will be low when compared with the value of the bandwidth in the wide band pass filter. Band elimination filter. Band elimination filter is also called as band stop filter or band reject filter also. And the band elimination filter operation is exactly opposite to the operation of band pass filter. There it passes one particular band of frequencies in band pass filter, whereas in case of band elimination filter it rejects only particular band of frequencies. That's why what I am telling is just exactly opposite operation of the band pass filter is treated as band elimination filter. Like the types in the band pass filter, here also we are having two types. First one is wide band elimination filter, and the second one is narrow band elimination filter. And here also, depending upon the value of Q, we are going to identify whether it is the narrow band elimination filter or wide band elimination filter. If Q value is less than 10, then we will be treated it as wide band elimination filter. If Q value is greater than 10, then we will be treated it as narrow band elimination filter. And the bandwidth of the narrow band elimination filter is very small value, and the narrow band elimination filter is also called as notch filter. Okay, and the wide band elimination filter bandwidth is high when compared with the notch filter. Okay, and the minimum center frequency will be calculated by using the formula FC is equal to square root of FL into FH. Okay, now coming to the first type in the band elimination filter, which is nothing but band rejection filter. Okay, which is nothing but a band rejection filter. Whenever the Q value is less than 10, then you will be treated it as a wide band rejection filter. Like wide band pass filter, here also we are having a low pass filter as well as high pass filter. Additionally, we are having a summing amplifier. Okay, with this circuit we are going to design the wideband reject filter. Okay, to satisfactory operation we required two conditions. What are they is, in the wideband pass filter we have seen it that FH is greater than FL in wideband pass filter, whereas wideband reject filter L is greater than FH, which is nothing but wideband reject filter. That is the main difference between the wideband pass filter as well as wideband reject filter. The first satisfactory operation of this circuit, the first one is the lower cutoff frequency should be greater than higher cutoff frequency, and the second one is the pass band gain for both the high pass and the low pass sections will be exactly equal. If you follow these two rules, then it will operate like a wideband rejection filter. And one more thing is, here I am treating that summing amplifier gain will be equal to 1. Gain of summing amplifier will be equal to 1. And for the calculation easy purpose, we are considering R2 will be equal to R3 will be equal to R4 will be equal to R. If you are treating like this, then automatically you will get the gain will be equal to 1. And here the R compensation resistance which is connected to the non-inverting terminal of the summing amplifier will be taken as R2 parallel, R3 parallel, R4, and the overall operation of the wideband rejection filter is depends upon the individual operations of the low pass filter as well as high pass filter sections. And like what we have seen it in the wideband pass filter, if you want to get the first order wideband pass filter, then you have to use high pass filter is first order as well as low pass filter is also the first order. Similarly, if you want to generate the first order wideband rejection filter, here also you have to consider both low pass filter as the first order as well as high pass filter is also the first order, and the output of the low pass filter and high pass filter will be applied as a input of the inverting input of the summing amplifier. From that we will be calculated the total output. From that output also we can calculate the transfer function of the system. Okay, and whatever the design steps you have used for the construction of low pass filter as well as for the high pass filter, the same steps here also you have to use for the construction of wideband rejection filter. That's already I discussed about the first order low pass filter as well as first order high pass filter analysis. That's why once again I am not representing those equations in this case, but while you are going to write in the exam, you have to write the magnitude functions of both high pass filter and low pass filter. That will be applied to the summing amplifier. From there we will be calculated the output voltage of wideband rejection filter. Similarly, if you want to generate the second order wideband rejection filter, then you have to consider both high pass as well as low pass sections are of second order type, and the outputs will be applied same as is that of summing amplifier. In that case also I want to represent the frequency response for the wideband rejection filter. So here, while you are going to represent the frequency response, always you are going to draw the frequency response in between gain and frequency. So you will get like this. So here it is pass band, and here also we are having pass band. That means it consists of two pass bands and one stop band. This is the minimum gain frequency which will be calculated as square root of FL into FH, and which is nothing but FH, and which is nothing but FL. Okay, so it eliminates particular band of frequencies. That's why we are calling it as a band rejection filter, and it consists of two pass bands and one stop band, and the bandwidth of the band elimination filter is very very small. Okay, coming to the all pass filters. The filters which are discussed till now are used to adjust the magnitude of the transfer function of the circuit. But this also alerts the phase angle characteristics. It is many times required to control the phase response of the filter. Filter which is used to control the phase response by adding a phase shift between the input and output signal is called as all pass filters. Its gain is 1. That's why it passes all the frequencies which we are applied at the input of the filter. It does not provide any attenuation, but it produces the required phase shift. For example, when you are passing the signal to the transmission lines, then there will be a phase shift generated between the input and output signals. To compensate that phase shift, we are going to be add the all pass filters in the transmission lines, which will be compensate the phase shift between the input and output signals. That's why we are calling all pass filters as a phase correctors also, as well as all pass filters as delay equalizers. Analysis of the circuit. To find out the output voltage, we have to use the superposition principle for this circuit. So first I am going to be assume the non-inverting input terminal is connected to ground. Then this circuit will act as a inverting op amp, and we all know that the output voltage of the inverting op amp is V01 will be taken as output voltage for the inverting op amp. Okay, so minus of RF divided by R1 into Vin. So here RF is equal to R1, so we will get it as V01. So next, now case 2. When we are connecting the inverting input is connected to ground, then this total circuit is acts as a non-inverting op amp. So while you are going to calculate the output voltage of the non-inverting op amp by using this circuit, V0 of 2 will be equal to 1 plus RF by R1 into VA. Here you have to calculate the value of VA, and RF is equal to R1, so you will get it as V0 of 2 is equal to 2 into VA. Now first calculate the voltage at node A by using voltage divider rule. VA is equal to Vin into minus JXC divided by R minus J into XC, which will be equal to Vin into 1 by J into 2 pi FC divided by R plus 1 by J into 2 pi into FC, which will be taken as Vin divided by 1 plus R J 2 pi into FC, which is nothing but VA. Substitute that value of VA in this expression, then you will get V0 of 2 is equal to 2 into Vin divided by 1 plus R into J into 2 pi into FC, which is nothing but V0 of 2. So to calculate the final output voltage V0 will be equal to V0 1 plus V0 2. Why? Because here you have used the superposition principle, and here you calculated the V0 1, which is nothing but minus Vin plus 2 into Vin divided by 1 plus Rj into 2 pi into FC. So take common as Vin, then you will get it as minus of 1 plus R J 2 pi FC plus 2 divided by 1 plus Rj into 2 pi Fc. From this, V naught is equal to V in into 1 minus Rj into 2 pi Fc divided by 1 plus Rj into 2 pi Fc, which is nothing but V naught. Okay, which is nothing but V naught. So if you calculated the magnitude, V naught by V in is equal to 1. Why? Because square root of 1 plus 2 pi FCR whole square divided by square root of 1 plus 2 pi FCR whole square. So the magnitude is equal to 1. Already I told you that when I started the all-pass filter, the magnitude of the gain of the all-pass filter will be equal to 1. That's why we are passing all the frequencies which we are applied at the input of the all-pass filters. So the gain is also taken as magnitude in this case, so which will be equal to 1. So while you are going to calculate the phase angle, okay, the main intention for the all-pass filter is we require the phase shift. Okay, so the phase angle phi is equal to tan inverse of imaginary part by real part minus of 2 pi Fc into R divided by minus of tan inverse of 2 pi Fc into R. Tan inverse of minus theta is equal to minus tan inverse of theta. So we will get it as minus 2 into tan inverse of 2 pi Fc into R. Using this analysis, what we can conclude is the gain of the all-pass filter is equal to 1 and the phase angle is equal to minus of 2 tan inverse of 2 pi Fc into R. Negative phase shift indicates V naught lags by V in by the phase difference phi, and the positive phase shift indicates V naught leads the input by 5 radians. And one more important point I want to tell you is, if you want to get the positive phase shift, just have to interchange the positions of R and C, then you will get the positive phase shift. And here I am going to represent the input and output waveforms for the all pass filters. Okay, and here it is time, it is magnitude, and here I am representing it as input signal, and the output signal is phase shift with respect to the input signal. Which is nothing but output, and here which is nothing but the phase difference phi, and these are the input and output waveforms for the all pass filter. Balanced modulator. In the IC version, the IC numbers 1496 and 1596 are used as a balanced modulator ICs. And first I am going to explain the basic principle behind the balanced modulator. We are all very well known that balanced modulator accepts two frequencies. Okay, one is modulating frequency and the other one is carrier frequency, and we are all very well known that the carrier frequency is having the highest frequency than the modulating frequency, and the balanced modulator produces the output as a sum and the difference of the input signals which we are applied at the input of the balanced modulators, which are Fc plus or minus Fm, where Fc is nothing but the carrier frequency and Fm is nothing but the modulating frequency. From this, what we can conclude is which eliminates or which suppresses the carrier signal and which produces the DSB signal is nothing but the basic principle behind the balanced modulator. Now I am going to explain IC 1496 or IC1596 IC version of balanced modulator. Here I have shown you that the 14 pin IC1496, and if you observe the pin diagram, the pins 1 and 4 are used to apply the input signal. Okay, so if you want to apply the modulating signal, you have to apply the modulating signal by using the pins 1 and 4, and the pins 2 and 3 are used for the adjustment of gain. Depending upon the application, sometimes you require the high gain and sometimes you require the low gain. So by using the pins 2 and 3, we are going to adjust the gain. And coming to the pin 6 and 12, while you are going to collect the output, which is nothing but double sideband output, if you want to collect by using the balanced modulator, you have to collect the output across the pins 6 and 12. And coming to the fifth pin, which is nothing but the reset pin. Whenever the sixth pin is connected to ground, then it overrides all the operations of the balanced modulator. And coming to the seventh pin as well as the 11th pin, they will not be used. That's why here I represented it as no connection. Similarly, 9th pin are also no connection. And coming to the 8th pin and the 10th pin, the balanced modulator requires two input signals. One is modulating signal and the other one is carrier signal. Already we applied the modulating signal by using the pin numbers 1 and 4. So by using the pin numbers 8 and 10, we are going to apply the carrier signal to the balanced modulator. And coming to the pin number 13, we will not be used that pin number 13. That's why I represented here it as a no connection, and pin number 14 will be connected to VEE. Okay, this is about the block IC version of balanced modulator IC1496. Now I am going to explain the circuit diagram of this balanced modulator, how the internal architecture of IC146 is constructed. With the help of this circuit diagram, I am going to explain the operation of balanced modulator. Okay, here the transistors Q7 and Q8 along with the diode are used for the generation of constant current source. Okay, listen carefully. The constant current source is generated with the help of transistors Q7, Q8 along with the diode. And see this, transistors Q1, Q2 and Q5 are used for the generation of differential amplifier. And the transistors Q3, Q4 and Q6 are used for the generation of another differential amplifier. Okay, so these three transistors are used for generating one differential amplifier, and these transistors are used for generating another differential amplifier. The carrier signal is applied in phase as a biasing signal of the differential amplifier. Okay, and the modulating signals are applied to the bases of the transistors Q5 and Q6. Okay, and these two transistors are in the current paths to the differential amplifier. So the variation of the current is depend upon the modulating signal which we are applied at the base terminals of the transistors Q5 and Q6. Generally, the equal current will be passing or equal current will be applied to both the transistor because of the constant current source. But the variation of the current applied to the differential amplifier is because of the modulating signal present to the bases of the transistors Q5 and Q6. The currents Q5 and Q6 produced by the transistors are 180 degrees out of phase to each other. That means if the current produced by the transistor Q5 is increases, then the current produced by the transistor Q6 is decreases, and vice versa. If you observe the circuit, the output is connected in parallel, okay, and while you are going to receive the output, you are going to collect the output across the collectors, and due to the balanced modulator operation, it cancels the common signal and generates the difference signal only. Because of this, it suppresses the carrier signal and generates the double sidebands at the outputs. That's why we are treating it as a balanced modulator. Into the applications of IC 1496, used as a balanced modulator, and the second one is used as a AM detector, and the third one is used as a AM modulator, fourth one is used as a product modulator, and the fifth one is used as a mixtures also, and the last but not the least, sixth one is used as a frequency doublers. In all these applications, we are using the balanced modulators.